So record this. Okay, so let's go ahead and get started. Our next topic, equilibrium and Le Chatelier's principle. So this is chapter 16 in the textbook. What we're going to do is establish sort of the rules of what equilibrium means, and we're going to talk about some important properties of equilibrium that will relate to our coming lab and the other lectures. So again, the course is designed to kind of build on itself. So this is going to be important for things coming up in the course. So first of all, technically speaking, we call equilibrium dynamic equilibrium. So we'll get into that. So dynamic equilibrium is important for reversible reactions, a reaction that can proceed in the forward direction or the reverse direction. So first we want to lay down some terminology so that we're all on the same page. So going forward for a chemical equation is reading it from left to right. And in that sense, we call moving in the forward direction the right direction. If we want to discuss the reaction going backwards, the reverse direction, then we read the reaction from right to left. We call that the reverse direction, or also the left direction. So we're talking about sort of directionality, right versus left. So whenever we're discussing what direction does the reaction go, is it going forward or is it going to the right, means that the reactants on the left-hand side are being used up to make products on the right-hand side. But if we're saying the reaction goes in the reverse direction or the reaction goes in the left direction, we're saying the things on the right-hand side are being used up to make the things on the left-hand side, right? Okay. Dynamic equilibrium for a chemical reaction is the condition in which the rate of the forward reaction equals the rate of the reverse reaction. So we can think of these happening simultaneously, back and forward, back and forward. When we get into equilibrium, we're going to discuss that some things are going to come into balance. One of those is the rates of the reaction. But before we go more into it, you might be wondering, why is it that some reactions are reversible in the first place? So how is it possible that things go back and forth? Well, now that we've talked a little bit about kinetics and specifically mechanisms, we remind ourselves about the energy diagram, the reaction coordinate energy diagram. Remember, a simple one looks kind of like this. Again, the reaction coordinate is not a measurable axis. It's just the beginning to end of the reaction. The reactants go over in activation energy to become products. And we said that as an analogy, think of it like hikers traveling up a hill and they need some energy to get over, but if they do, they become products. And that hill they have to cross, we see it here, is our activation energy. But using that same logic, well, what's to stop the hikers from trying to go back over the hill, to go back where they came from? And what it turns out is that if this energy diagram is drawn in a way, or it is such that the energy it takes to go backwards isn't that bad, isn't a big deal, then we would have a situation where some of the hikers actually travel down. So we'll get this exchange happening. So reversible reactions can occur when the activation energy in both directions, going up the hill in both directions, is reasonable to do at room temperature or whatever temperature we have. So the idea behind why reactions are reversible goes back to our discussion of Module 1 and mechanisms and the energy involved in why reactions go forward and at a certain rate. But speaking of equilibrium, let's rationalize why equilibrium happens and what is going on using what we know from our kinetics discussion. So let's sort of establish this with a simple reaction. Let's say it's a one reactant going to one product, an A goes to a Z. And it's reversible. So here's our reversible arrow. And A will go to Z with a rate constant of K1. And Z goes back to A with a rate constant of K minus 1 to say reverse. And this is a one-step mechanism. A just makes Z, Z goes back to A. One thing that we can establish is what's going to happen with our concentrations of each over time for, again, a one-step reaction like this. So first of all, let's remind ourselves about last time. Let's write the rate laws for the forward direction and the rate law for the reverse direction. So remember how to do that. This is a one-step mechanism. A just goes to Z. So what would we write down for the rate law for the forward direction? And what would we write for the rate law of the reverse direction? R is equal to what rate law? What comes after R? R equals?
K.
K, yeah, K times, now in this case, we're going forward. So the reactant in the forward direction is our A, right? So in the forward direction, the rate law would be R forward, and I'm putting F for forward, equals K1 times A. And our rate law in the reverse direction, if we read it backwards, R equals K minus 1 times Z, right? So we're always writing rate laws in terms of what is being used to go in that direction. So it's always going to be the reactant in that case. So in the case of going reverse, the reactant is Z. Okay, so these are our steps. Now, quick review. If these are our rate laws, which they are, then what type of order do we have for these processes?
Is it first order?
It's first order. Yes, it's first order. So when we think about the concentration change over time, does it make sense to us that we'll start to use up some A if we start our beaker with A? We start some A, it'll start getting used up. But what do we, at a certain rate, I should say, at a certain rate. But as we start using up concentration of A, according to first order, does the concentration affect how fast we go? Yeah. So it should make sense that over time, the concentration of A will decrease, but it's not going to be decreasing linearly. And we saw that in our last two lectures ago. It's not going to decrease linear. It's going to decrease with an exponential decay. So it's going to start decreasing. And because of the one-to-one stoichiometry, for every one A, you make one Z, then the concentration of my product is going to go up in that amount. But as we know, with first order, the rate of A is going to slow down, or the rate forward, I should say, is going to slow down as the concentration of A decreases. But this is a reversible reaction, which means it can go backwards. So as this reaction goes forward, we are going to start making Z's. So the concentration of Z is going to go up. So again, according to first order, as the concentration of your Z goes up, the reverse process is going to get what? Slower or faster? As the concentration of Z goes up, for a first order reaction, we see a first order rate law. The concentration of Z goes up, the speed of this process is going to go up, right? It's going to go up as well. Yeah, exactly. Thank you. It's going to get faster as well. So what we have here for a reversible reaction, we start with a beaker of A. We're going to say it's going to start quickly using up my A to go forward, and we're going to make product. But then, since this is a reversible reaction, as I start building up, and that's what this picture is showing, as I start accumulating more and more Z's, then the reverse process by first order, the more Z's I have, the more it will probabilistically go backwards. It's going to start getting a faster rate going backwards. Eventually, they are going to, meet in the middle, where the rates of the forward direction and the rate of the reverse direction will be equal to each other. So at any moment in time, for every one A that I turn into a Z, another Z is going to turn into an A. And so at that point, we see what we call equilibrium being reached. And that's what's being shown here at time labeled as the equilibrium time, T equilibrium. If we have exactly the same rate for each process, one A becomes one Z, and at the same time, one Z becomes one A, there's going to stop being changes to the concentration. And so graphically, we say equilibrium is when the concentrations become constant. So we would label this marking we're labeling is A equilibrium and Z equilibrium. We come into balance. So equilibrium is all about balance. What we've shown is that at equilibrium, this balance point, there should be some point in time where the two processes of going forward and backward will eventually balance each other out. The rate of the forward will equal the rate of the reverse. And when that happens, the concentrations will stop changing because they're exactly balancing going forward and going backwards. Okay, so there's one more thing that I'd like to leave us off with before we leave, and that's this equation, R forward equals R reverse. It is the special point where we say we've come into balance, but there's something else special about it that we'll appreciate more in the next slide. And that's starting point is by setting these two equal to each other, setting this equality equal to the rate laws. So notice I've just substituted the right-hand side of each rate law. What we find is that if I do a little bit of manipulations, I'm going to move my Ks to one side and I'm going to move my concentrations to one side. We will get a ratio of product Z to reactant A that is equal to the rate constants ratio for those processes. Now, the rate constants themselves are just constants, they're just numbers. So it tells us that our ratio of concentrations inside our beaker eventually will become constant. And so ratio of product to reactant is going to be constant when we reach equilibrium. And that's not going to sound too fancy right now, but it will be important later on. Oh, interesting. The ratio of products to reactants are going to be a constant. Let's actually see why this is important. Let's try this scenario again, but using the same reaction, but at different initial concentration. So what I have here is two trials, trial 1 and trial 2. And what you'll notice as the difference is that the starting amount of A is higher up in concentration and the starting amount of A in the second trial is a little bit lower in concentration. What would be special about this case, or if anything? Well, so I'm putting here a reminder of what we had from our previous slide. We'd say that if this is a one-step reaction, we have our rate laws based off of those steps, and it came out that we plateaued when the rates got equal to each other, which gave us this answer. And that was the last thing we wrote on the last slide. What if we did the exact same thing for a different starting concentration? So you might think that, yeah, wouldn't we start it the same way? Well, we say, well, regardless of the concentration, we're going to start by using up A pretty quickly, and then it's going to start making Z's, causing the reverse reaction to start to speed up. And wouldn't that mean they'd end up being equal to each other? And then the rearrangement would look something like this again. It turns out that that is true. That is true. But we realize there's now something special about this. No matter what our initial conditions are, the series of thought process will always be the same, and the math associated with that will always result with the ratio of concentrations at equilibrium will equal not just a constant number, but the same constant number every single time. So no matter which starting amounts I use, it'll end up being that the ratio of Z over A is going to be equal to K1 over K minus 1. And those are just constants. Those are just the rate constant ratios. So that means we'll get the same answer at equilibrium every single time. So that's telling us there must be an important mathematical relationship among the equilibrium concentrations. If I have a reversible reaction, there is something special about the concentrations when I get to equilibrium. Whoa, that's crazy. So let's go ahead and establish what that is. That special ratio is a number that we are going to have a lot of, spend a lot of time with. So let's go ahead and get to it. This is called an equilibrium constant, capital K. Sometimes it's more specifically labeled KEQ for equilibrium constant, but that EQ is optional to write. And I apologize in advance because we just got through a module where we were using a lowercase k, and now we're in another module where we're using an uppercase k. We need to now be careful to use the correct notation. So capital K is something new. Capital K is an equilibrium constant. It has special properties. It can help us quantify which direction is more favorable when equilibrium is achieved. And to illustrate how it's set up, there is a special sort of consideration to write an equilibrium constant. We said it had to do with the amounts at equilibrium. It is specifically for a reaction. It is shown here. What you're seeing is it is the product, meaning multiplication, the product of the product concentrations at equilibrium raised to their coefficients as an exponent divided by the concentration, the product of the concentrations of reactants at equilibrium raised to their coefficients. So this is how we define that special ratio in the case where we have more than one reactant or more than one product. If we have coefficients in our balanced chemical equation. One thing to note is that we're very specific to say concentrations. So things that are pure solids or pure liquids, like liquid water, for example, are omitted because their concentrations remain constant over a reaction. The moles to volume ratio for a solid and a liquid will always be the same due to density considerations. So if they're always going to be the same, then we don't need to put them. So this ratio only applies to solutes or gases. So the ratio of the total product concentrations, or if you're doing a gas reaction, you can also substitute this for partial pressures. So it'll be the pressure of gas A to its coefficient over the pressure of whatever that may be, which substitute with the chemical symbols. So that is our equilibrium constant. This special number that happens when a reaction, reversible reaction, comes into balance. Okay, so far, reactions can be reversible. When reactions are reversible, as we start to accumulate product, it goes backwards to make reactants. And there's this special moment in time when the rates match each other and concentrations stop changing. And there's a special relationship to those concentrations at that time. The ratio of those equals a constant, the same number every single time. And we call that the equilibrium constant. Okay. So some already interesting things about the equilibrium constant. So first of all, we're talking about this number at the moment that we reach dynamic equilibrium. So what is that specifically spelled out? Dynamic equilibrium for a chemical reaction is the condition in which rate of the forward reaction matches the rate of the reverse reaction and concentrations no longer change. I would just like to emphasize that equilibrium means balance. It doesn't mean stop, and it doesn't necessarily mean equal. So we say, oh, look, my concentrations don't change. That doesn't mean that there's stillness in the beaker. The little molecules are moving around all the time. What it means is that the amount of reactant going to product balances out the amount of product going to reactant. So the reactions do not stop happening. It is dynamic. Dynamic means moving. It is dynamic. So that means that while they are still moving, the rates completely balance each other. And the same thing with equal. Balance doesn't necessarily mean equal. And we can show it in these two graphs momentarily. You see that the concentrations start to change because the reaction is happening. They come into balance. We see them plateau. But clearly, the amount of reactants, the amount of products are not necessarily equal. So one thing that the equilibrium constant actually helps us do is figure out what is, whether or not we expect a reaction to make products to a certain extent or not. And so in this particular case, we could think about it. And then I see a question in the chat. I'll come back to that question in just a second. So first of all, we take a look at our two graphs. X reversibly goes to Y, and M reversibly goes to Q. And we see, whoops. So we see the equilibrium amounts at the end. We see where we plateau. Now, the first question I'll sort of pose to you guys is, for the first graph, does it look as though the reaction came into balance at the point where we made a lot of product, or did it come into balance before we made a lot of product? We still have a lot of reactant. Does this graph suggest that we make a lot of product or not? No, yeah, thank you. Yeah, no, it doesn't look like that at all. So when that happens, if we come into balance and we don't make a lot of product, we say we still have a lot of reactant left over, and the concentration stopped changing. We call that reactant favored. So this is a reactant favored equilibrium because it went forward only a little bit and we still have a lot of reactant by the time we've come to balance, by the time we've come to equilibrium. Now, another question we can ask is, what does this suggest about the equilibrium constant itself? So we remind ourselves, we come into balance, we say there's a special number that's associated with equilibrium. The ratio of amounts is going to be equal to a special number every single time, an equilibrium constant. If we set up that ratio, products over reactants, we're going to get Y at equilibrium divided by X at equilibrium. If we have a reactant favored equilibrium, we have a lot of reactant left over at the end. This suggests that this ratio will have a bigger bottom number, a bigger denominator than the top number. Or thinking about it in its, on the number line, it's going to mean that this ratio is going to be less than 1. So one thing we can say is that the equilibrium constant can give us, by the size of the number itself, an idea of whether we should expect there to be a lot of product when the reaction happens or a little bit of product. If we have a reactant favored equilibrium, not much product is made, then the denominator of my fraction is going to be bigger than my numerator. I will get a number less than 1. So numerically, we say if a reaction has an equilibrium constant less than 1, I should expect that I'm not going to make a lot of product from this reaction. It's going to be a reactant favored equilibrium. Okay. What about the other graph? In this graph, what do we have? We have a situation where M is our reactant and Q is our product. We see that we've now used up almost all of our M and made up almost all of our Q. So we're looking at our graph and we're looking at what is happening to the reactant and what is happening to the product. That's how we figure out whether it's reactant favored or not. So in this case, we use up all of my product, and now I have a majority of, or sorry, use up all of my reactant, and I have a majority of product. So therefore, I have now a different situation. This is called my, whoops. This is called my product favored equilibrium. So the way we can tell a reactant favored from a product favored equilibrium is by the relative changes from beginning to equilibrium. In the first graph, we started with a reactant. We did not use up a lot of reactant. We have much more reactant than product at the end. So this suggests that the reaction didn't go forward that much before it came to balance. So that's how we know this is reactant favored. Whereas in this graph, we see we used up a lot of our reactant, our purple line, and we have much more product at the end than reactant. So we used up a lot of reactant to make product. So that's how we know now this is product favored equilibrium. So again, using the idea of equilibrium constant is a ratio of amounts. This time, if I do products divided by reactants, the numerator is much bigger than the denominator. So I should get a number that is greater than 1. So now we can establish a way to interpret an equilibrium constant. An equilibrium constant is a special number that goes with a reaction that is reversible. And if the equilibrium constant is less than 1, I should expect this to be a reactant favored equilibrium, and it won't make a lot of product. Or if the equilibrium constant is much greater than 1, then I expect it to be a product favored equilibrium. And I should expect to make a lot of, have relative, speaking in relative terms, a lot of product compared to reactant. I'll make a lot of product in that case. So equilibrium constants, the first thing we can use them for is just looking at their size and telling whether we have a reactant favored equilibrium or a product favored equilibrium. We expect to have more reactant than product in a reactant favored equilibrium at equilibrium. In a product favored equilibrium, by the size, we should have more product than reactant. The other question that was mentioned in the chat that I'll go back to now is when we do this ratio, does the equilibrium constant have units? And the answer is no. The equilibrium constant does not have units, even if, so what that means is you don't have to try to do dimensional analysis for an equilibrium constant. And the textbook goes into more detail. It has to do with the fact that due to having reference measurements involved in the calculation, that's not really a detail that really is important to me that you know. So all you need to know is that you don't have to worry about units when you calculate K, no units. Okay. Another question, are all reactions reversible to some extent? Yes and no. So specifically, reactions that maybe involve collisions within a solution perhaps are a good candidate for being reversible, since they can float back together and hit into each other and maybe do the reverse of what they did before. But there are some reactions that statistically, probabilistically, there's no way they can go backwards. And a good example of that is combustion, right? So you take like a fuel, like a really long hydrocarbon, a fuel that has lots of carbon atoms connected together with hydrogen atoms along the chain. And you add oxygen to it, they break apart and you make CO2 and water. It is extremely, extremely unlikely, to the point where it's zero chance that the CO2 and the water would come back together and make the fuel molecule again. So there are definitely reactions that we can say are safe to say they're irreversible. And combustion is a good example of it. It's just probabilistically the likelihood that you would get the same chain of events to get your gas molecules, which are now floating in all over the place, to come back together is extremely, extremely low. So yeah, there are some irreversible reactions that definitely are safe to say are irreversible. But there are a lot of reactions that are reversible. And we'll deal with a lot of those. Acid-base reactions are reversible, for example. We'll talk about those. So yeah, when it comes to irreversibility, think about it. What is the probability that the products could get back together to make reactants? And there's some reactions where it's like not reasonable to think so. So there are some, but not all. Okay, so equilibrium, reversible reactions, they come into balance. They don't necessarily go all the way to products. There's a special ratio that we can calculate to show that they've come into balance, an equilibrium constant. That's a constant. Every time we get to equilibrium, our ratio of products and reactants make that number. What about if we get to equilibrium and we disturb it, which is something that happens all the time in nature? Well, let's think about what's going to happen each time. So first of all, let's establish, given enough time, reversible reactions will reach equilibrium. So think of it like a scale. Not necessarily the scale is equal, but rather the scale stops moving. So sometimes the scale isn't all the way 50-50, but you might have more products than reactants at balance, or more reactants than products at balance, and that's okay. It just means we're in balance. At this point, any further changes out from the outside world are considered a disturbance to equilibrium. And those include changing concentrations of reactants and products by maybe adding more or taking away, or changing partial pressures, changing the temperature, or changing the volume of the system. So the question we want to ask for the remainder of this lecture is, how does equilibrium reaction respond to disturbances? And so the first one we'll talk about is concentration disturbances. But disturbances in general is the focus of the remainder of this lecture. So we have a guiding principle for what to think when this happens. It's called Le Chatelier's principle. When a chemical system is disturbed from its equilibrium position, the system shifts in the reaction direction that minimizes the disturbance. So let's take a look at what happens when we disturb a reaction at equilibrium. So we have a reaction, a simple one, R goes to P. We're reminding ourselves that the R is the left-hand side and the P is the right-hand side. And we see our graph right here. We've reached equilibrium because the concentrations have plateaued. And we want to see what happens if we disturb the equilibrium. So the first thing we want to say is, let's have off to the side what our equilibrium condition is. We have a special number that we reach when we're at equilibrium, the equilibrium constant. In this case, when the balanced chemical equation is 1R makes 1P, According to the formula for equilibrium constant, what is K equal to? Capital K is equal to what expression? What goes on the top? It's the ratio. It'll be P over R. Yeah. So let's keep that in mind. Yes, perfect. Thank you. So the equilibrium expression for this example is going to be the concentration of P at equilibrium over the concentration of R at equilibrium. Now, let's see what happens if I apply a concentration disturbance. My reaction is in balance. The forward rate and the reverse rate have equal each other. So now the concentrations have stabilized. Everything is good. Suddenly, I'm going to drip in some extra reactant into my beaker. So that's what you see here on the graph. So at time point, well, I didn't label the time point, but at a certain point in time, I'm just going to squeeze a little bit more out of the dropper into the beaker. So my concentration of R suddenly goes up. So now the question is, am I still at equilibrium? Well, let's think about how it affected the ratio. If I have products over reactants have to be equal to this number, and I'm already at this number, then what did I do to this ratio? Did I suddenly change it so the top is too big relative to the bottom, or vice versa? Which part of this fraction is too big? It would be the bottom of the fraction, yeah, right? Yeah, the bottom of the fraction. So this ratio is now not the correct ratio. We already had it perfect. But if I make the top too big without changing anything else, then this is not the correct ratio anymore. So what I'm going to have to do is change things around, start shifting things around in order to come back to equilibrium. So if I have too much R now in the beaker relative to P, I have too much R now. What process would have to happen to help fix it? Would it make sense that I need to go forward or to the rightmost direction? Or would it make sense that my reaction would fix things by going from the right direction to the left? Yeah, goes forward, right? Yeah. So if I go forward, I'm going to use up some of that extra R to make P until my reaction comes back to equilibrium. So the rate of my reaction will start to adjust. Exactly. You guys are right. Perfect. Thank you. And thank you so much for your participation in the chat. Yeah, exactly. We're going to use up R to make more P. And that's exactly what's happening. Our rates now change so that I start using up more R. And as a result, it's going to start making more P. And it will do the exact same thing that we did in our first slide. The first order kinetics will continue until the two rates meet each other again. And when that happens, we'll plateau one more time. And so we get new equilibrium concentrations, but we know for a fact that the concentrations change by the kinetics. They change until we get back to this same number again, this same ratio. So the fact that we've plateaued means that the ratio, again, of product to reactant is back to being equal to the equilibrium constant. So to recap, Le Chatelier's principle tells us that if a chemical system is already at equilibrium, if we disturb it, the reaction tries to minimize the disturbance. And in the case of this example, if it was in balance and we added too much R to it, it's going to use up the R to make more P. So it always tries to push away from the disturbance. So we use up our R to make more P until we come back to the correct product amount to reactant amount ratio. And the same thing can happen if we disturb any concentration or if we disturb it in any direction. And as an example, here's an example where now we'll disturb how much P is in the beaker, the product. And this time, instead of adding more, we'll take away product. So one more time, we'll ask the question, we were already at equilibrium, so now we've disturbed it. We're no longer in balance anymore. We're no longer at equilibrium. So how will the reaction respond to try to minimize this issue? We have taken away some P that helped us be in balance. What are we going to have to do in order to fix this? Are we going to have to move to the right-hand side, take reactant and turn it into product, or left-hand side, take product and turn it into reactant? So is the reaction going to shift to the right or shift to the left? And absolutely correct, the reaction shifts to the right or we move forward. Yeah, we're going to have to add more product back to get things better. So the reaction will start to change the rates again. The reaction moves forward and uses up more reactant to gain product. I like to think of it as when you have a disturbance where you remove something, is you've kind of created a hole, a not literal, a figurative hole that needs to be refilled. So if I remove P, I've created a hole on the right-hand side of the reaction. So the way to refill it is to take some R and add more P to the other side to make more P. So the reaction shifts to the right or shifts forward to minimize the disturbance. And so what we see is that we don't get the same amounts that we did before. And I'm showing that with this bar graph here of the before equilibrium amounts versus, and I'll move that over there, the after equilibrium amounts. Notice that they're different, but putting them on top of each other, while the bars are literally different sizes, the ratio of those bars, red to the smaller red and blue to the smaller blue, the ratio of those are going to be the same. So equilibrium is still established. Oh, oops. Equilibrium is still established. So one thing that I would like to emphasize is we're careful to say with Le Chatelier's principle, a reaction will adjust to minimize the disturbance, but it does not undo the disturbance. It can't. So we come back into balance, but the actual amounts in the beaker are different than they were before. We minimize or adjust to minimize the disturbance, but the actual amounts are different. However, the ratio, the relative amounts are the same. So this is your opportunity to try it yourself. I'm giving you 4 example reactions, and I'm going to disturb these reactions. So how will the equilibrium shift when, and here are your options. And what the assumption is all 4 of these examples are already at equilibrium. They're in balance. And now we're going to do something to them. Can you tell me what direction the reaction wants to go to fix, to minimize, I should say, the disturbance? So the first reaction, if extra B is added, what will happen? Will the reaction want to adjust in the forward direction or the reverse direction, etc. So I'm going to give you guys an opportunity to try that. as I'll be right back. As I'll be right back. So give yourself an opportunity to try it, and then we'll talk about it. All right. So for the first one, the equilibrium reaction A goes to 2B. If this is already in balance, whatever it may be, maybe it's like this, maybe it's like this, doesn't matter, it's in balance. If I all of a sudden added more B to the reaction, what will it do? Will it shift to the right, or will the reaction shift to the left to try to fix? Let's see. It will shift left or shift to the reactants. It will use up some of my B to turn it back into A to come back into balance, right? It always tries to move away from the issue. So if there's too much B, it'll try to use it up to make A. For the next one, we have X plus Y aqueous makes Z aqueous. If Y is added to the reaction, now we have extra Y here, which is a reactant. It's going to have to shift right. Perfect. Yeah, not so bad, right? So it has to shift right or shift forward. It has to use up the extra stuff that it has been given so that it can come back into balance. It was already perfect. Now you have too much. So I'm going to go the other way. If Q is, and of course, if there are any questions about anything, please let me know. If Q is removed from the reaction, now this time we're taking away from one side. The reaction is going to go to the left. Yep, is going to go to the left to sort of refill lost reactant. So lost R means reactant, refill lost reactant. And then this reaction is at equilibrium. D is added to the reaction. Oh, no effect. Yes, very good. Yeah. So one thing that we note about equilibrium constants is that they're the ratio of concentrations. But solid is not something that has a concentration. So if we think about, we did add something to the beaker, but there's nothing to show for it in the math. It doesn't show up as either in the numerator or the denominator. So here is something tricky. Once a reaction has established equilibrium, we're concerned about equilibrium concentrations and equilibrium pressures for gas. A solid or a liquid does not have a concentration or a pressure. So the answer would be there is no effect. Oh, well, what happened if you had a different, so that's a different story. And actually we'll see an example of that. So this is all in the context of you're adding something that is in the reaction itself. We'll actually talk about what happens if you add a different solid. If this is a little bit confusing to you, I do have a real world example. And that example is dissolving, say, table salt in water. You can add spoonfuls of salt to water and watch it, stir it and watch it dissolve over and over, but there will be a point where you saturate your solution, right? There's a limit to how the solubility, how much salt can actually dissolve. So that would be considered a reaction at equilibrium. Now imagine taking another spoonful of solid and adding some more into a saturated solution of salt water. You will see it settle to the bottom and none of it dissolve. That is an example of what's happening here. If you had solid salt makes Na plus ion and Cl minus ion. If you were to add more salt to something that's saturated, we know from everyday experience that there's a limit. And if you add too much, it'll just sit at the bottom of the beaker. So once a reaction has reached equilibrium, adding a solid reactant will not do anything to it, just like adding more salt will not dissolve in its solubility reaction. Now, being supersaturated is a different story. Yeah, what happens with supersaturated? So supersaturated is actually you're not at equilibrium either, right? Because you've dissolved too much. So that would be a situation that that the universe does not like. But to be clear, and this is actually going to come up, the way that things become oversaturated or supersaturated has to do with something we haven't talked about. In all of these examples, we have an implicit assumption that temperature doesn't change. If the temperature changes, it actually does change things. And that's how supersaturated solutions are generally made. So supersaturated requires something else to happen outside of this. So assuming that temperature doesn't change, then this works. Then we get into this supersaturated case, their temperature has to change for that. And we'll see that effect in it. Oh, but the good question, if we add more E or G, would it shift? And the answer is yes, it will. If we add another anytime we add a solute, something will happen. What we would see is if we added more E, the reaction has too much product, it'll shift to the left. So what we would see is that some of my products would make more solid. We could actually see if enough has been added, we could actually see solid reform in that case. So yes, we would see a shift if we added more E or G to this beaker. But we would not see anything happen to the concentrations if we added more D to the container. Good questions. Keep them coming. Hey. Actually, the next slide is speaking of temperature. So yeah, it's all about what happens to something that's come into balance, what happens when we disturb it. So the next thing is temperature. Temperature depends. There is no black and white sort of, yes, no answer to what does temperature do. It actually depends, and what it depends on is the enthalpy of the reaction. So we need to be given the enthalpy of the reaction to answer what will happen. But we treat this as we've treated disturbances in the last few slides. For an exothermic case, delta H is less than 0, negative numbers for enthalpy. Exothermic, we release heat, so we treat heat as if it were a product in the reaction. We could even write it there to help us with the analysis. If it's endothermic, so delta H is a positive number, we're absorbing heat. We treat heat as a reactant. And so with this in mind, if we're adjusting the temperature, we would say things like, if I lower the temperature, it's like I'm removing heat. And if I'm raising my temperature, I'm like adding heat. So if I were to have an exothermic reaction, and I said, I made this equilibrium reaction hotter, it would be as if I added product to my I added more product. In this case, adding more product, I need to use up that product. It will go to the reverse. And if I said I added more heat to an endothermic reaction, I would treat it like adding a reactant. The reaction needs to use up that side. It will go shift to products to make that happen. And so that's the basic idea. It depends on whether it's exothermic or endothermic. And we treat heat or temperature changes as if we're adding to one side or taking away from one side. However, and this is where it gets into the idea of supersaturation. The other thing about temperature is that temperature is a source of energy for particles. So that actually affects how many of those particles can actually move from reactants to products or products back to reactants. So we think about our energy reaction coordinate diagram from last time, and the ball rolling over the hill or hikers going over a mountain. If we add more temperature, we're actually giving them the energy to roll over each side more easily. For the case of an exothermic reaction, giving the particles more energy gives them more opportunity to get over the taller barrier. So it's already easy for them to go over from left to right because it's a smaller barrier. But if it were going from right to left, it's a harder barrier. If I give them more temperature, I should expect it to really help out the particles going over the taller barrier. So more particles will go backwards. This result will make the ratio of products to reactants a little bit smaller. So K actually gets smaller. Temperature is the only kind of disturbance that will actually change the number value of K. And so that's sort of one of the hidden reasons why supersaturation can occur. It can occur with temperature changes because it actually readjusts what the correct ratio is when it comes into balance. And then with endothermic, it's the opposite. If I add more temperature, the side that had more trouble is the opposite case. It's the reactant to product side, and it'll make it easier for them to go over the hill. It makes the amount of products over reactants to be a little bit larger, biasing products a little more. It changes K to a larger number. Temperature is the only disturbance that actually changes the number value of K when we're discussing disturbances. And then I'd be happy to talk about actual sort of real life examples. I'm not familiar with supersaturated lakes or the one that's but I can look into it, but I don't know. Yeah. When it comes to gases, we can also talk about volume as one of the disturbances because gases like to take up volumes. So volume changes will directly result in changes to partial pressure, and by Le Chatelier's principle, the reaction will shift to relieve this partial pressure change. So the idea is reaction accommodates the different volumes. So there, again, with like temperature, there is no yes or no sort of always true answer. It depends on the reaction. What I like to think is the reaction will always try to accommodate a volume change. So we have a piston that has a reaction, two A's make a B, and perhaps we push down to make the volume smaller. How will the reaction respond to that? So I now have made my particles a lot more crowded. The reaction will try to shift to get rid of this issue. So all of the partial pressures have now increased a little bit as a result. So the way that we reduce that is to try to get rid of some gas particles. If I get rid of some particles, it'll be less crowded. Which side of my reaction has less gas particles? It's the side that has B on it. So the reaction will go forward, it will go to the right, using up two A's to make one B, so that there is overall less gas particles, and we make the system less crowded. So the basic idea, the reaction shifts to accommodate that change. So I made my reaction now a smaller volume. I shift to the side to decrowd the volume. Whereas if I increase my volume, now there's extra space, the reaction will shift to fill that extra space. So it'll shift to the side with more gas particles. So the idea is the way it shifts depends if the gas has been given extra volume, the reaction shifts to fill that extra space. So it'll move to the side with more gas particles. In this case, it'll go left. And if the volume decreases, it'll try to get rid of particles to make it less crowded. It'll shift to the side that has less gas. So again, it depends on the exact balanced chemical equation, which side has more gas, which side has less gas. And the idea is the reaction goes whichever way to kind of undo too crowded or too sparse. It'll try to fix that. The reason behind this is collision theory. Back to module 1. We think about, in order for this gas phase reaction happen, two A's have to collide to make B. If we make our volume a lot smaller, the probability of two A's colliding is now higher. It is more likely two A's will bump into each other to make a B. So the whole idea behind how this works can go back to what particles have to hit into each other. Does making the volume bigger or smaller make that less likely or more likely? So there's a connection to what we talked about before. Now, the last few slides are going to be sort of specific applications of Le Chatelier's principle. And specifically, I would just want to give a little post about this here, is that some of these are going to be relevant to our next experiment, which we'll do definitely next week on equilibrium and Le Chatelier's principle. We disturb something, what's going to happen? So the first thing that we'll look at is dilution, the effect of adding water to a reaction. So we have an aqueous reaction. One way we can disturb aqueous reactions is to add water to them. What effect does adding water to an aqueous system at equilibrium have on its position? So let's take a simple example. X aqueous plus Y aqueous makes XY aqueous. To sort of set us grounded on this, let's first write out what the equilibrium constant is equal to in terms of the ratio of the things in our reaction. So remember that it's always the same, product to its coefficient over reactants to their coefficients. So that's going to be XY over X times Y. Okay. So let's have that in the back of our minds as we think about what water is going to do. So let's say we added enough water to do a 10-fold dilution. So that means that we're going to have a 1/10 of the concentration. Now this seems odd. Water doesn't appear in the reaction, but what's happening is water affects the concentrations of everything that is dissolved in that solution. So even though water isn't in the equilibrium reaction, it does have an effect because water is a solvent. So here's something to keep in mind. Even though water might not be in a reaction, water is a solvent that can change the concentrations of things that are dissolved in the solution. And yeah, another way to think of it is it increases the volume. Exactly. That's a great analogy for that. So if we dilute by a factor of 10, for example, suppose we did, then what happens to the concentrations and what will happen to that ratio? every single thing in this ratio now has is decreased by a factor of 10. So upon simplification, what happened to my ratio? Did it get bigger, smaller, or stay the same? If we cancel and then move things around, right? There's a 1/10 that cancels, but one that doesn't. Our new ratio is 10 times the original correct ratio. So our reaction is too big. Our ratio is too big. So we consider what happened to the concentrations. Ratio is now too big. If it's too big, then what do we have too much of? Product or reactant? If our ratio is now too big, think of what's on each side of the fraction bar. Yeah, we have too much product. So again, so even though water is not a part of this reaction, it messes up everyone's concentration. And the result is that our reaction has to use up too much product. It has to go to the left. So the reaction shifts to the left. And one way to think of it, and it's a perfect connection. So thank you, Santiago, for that mention, is we can think of it a lot like the gas situation. Dissolved solutes, if we add more water, we're giving them more room. Just like in the gas example, we made the container bigger, the gas reaction wants to fill that extra space. So in this same idea, adding more water gives the solute particles more room. They want to fill that extra room. So dilution will favor the side with the most solute. And as we can see, in this example, the side with the most solute is the left-hand side. So the reaction will shift to the left. It'll go in reverse to fill that space. And mathematically, and we'll talk more about the math in our next lecture, mathematically, we can see that if we dilute every single concentration, the ratio is too big. So we have to use up some product to make reactant. So one thing to note is that dilution, adding water, will have some repercussions, even though water may not be in the balanced chemical equation. And even though it may be a pure liquid. Oh, and then my last comment is, what if we did the opposite? What if we did evaporation? So we start losing water as a solvent. Concentrations are going to do what if we evaporate? They're going to get higher, less volume for those particles. So the reaction is going to shift to the side with the fewest dissolved particles. So dilution and evaporation are sort of opposite processes, and they'll have opposite effects. Inert gases comes up a lot in some chemical reactions, so it's nice to know what will happen if we have an inert reaction. So just to go over really quickly, it's because the answer is nothing happens. So basically what it means is we have a rigid container with gases floating around in there. We inject some other gas that doesn't take part in the reaction. So commonly inert gases include noble gases. Nitrogen gas is commonly used as an inert gas because it is not very reactive. While adding more gas to a rigid container will increase its pressure, it doesn't affect the partial pressures of any species. And so if it doesn't affect the partial pressures of anything, it won't affect the equilibrium because both the reactants and the products have no changes to them. And I just present here a quick sort of proof that nothing changes using the ideal gas law and the equilibrium constant. So this is in terms of pressures. So if I have this reaction, two A's make a B, then the equilibrium constant is equal to the pressure of B divided by the pressure of A squared, because there's a 2 here. With the ideal gas law, the pressure is going to be equal to nRT over V. If I add enough gas to double the pressure, we have a few things that we know. The final pressure is going to be twice the initial pressure, and the final number of moles is going to be equal to twice the initial number of moles, because the direct relationship between them. If I have twice as much pressure, I must have twice as many gas particles. Anyway, the formula for, and this should all be something that's from Chem 1A. Again, I'm just showing this. It's not going to come up on quiz or exam, but the formula for partial pressure, the mole fraction times the total pressure. So this would be how we would calculate the partial pressure of A, the moles of A divided by the total initial moles times the total initial pressure. If I did the same thing for the after, the moles of A didn't change, but I have twice as many gas particles and I have twice as much pressure. Those twos actually will cancel. You end up with the same number. So therefore, no change happens to the ratio. No change happens to any of the pressures. Long story short, if you add an inert gas to a rigid container of gases that are at equilibrium, nothing's going to happen, even though it might seem like they do. There's the way we can prove it with our first semester knowledge of gas laws that nothing will happen. And I'd be happy to talk more about it. I know I just breezed through that, but I'd be happy to talk more about it after lecture. Now, a case that's going to come up in experiment 1. Adding a substance that yields a reactant or product ion. Let's say we have a beaker, and that beaker has HF. It's at equilibrium. What's going to happen if solid sodium fluoride, NaF, is added to a solution of HF, hydrofluoric acid, at equilibrium? What is going to happen? So first let's establish what's happening in the beaker beforehand. We said we have HF at equilibrium, so there must be some kind of equilibrium reaction present. So we think about what HF is. It's an acid. So we ask ourselves, what do we know that acids do when they get dissolved in water? Like, what does HCl do? Dissociates. Dissociates into what? It's positive H plus and the anion. So what would that be in this case? HF would split into H plus aqueous and F minus aqueous. So that would be the reaction when it says HF is coming to equilibrium. Well, what is it doing? It, like all acids, it splits apart. Now you might remember, you say, wait a minute, weren't we supposed to know something about weak acids? Weak acids don't really dissociate all that much. So what does this suggest about the size of the equilibrium? Is it product favored or reactant favored? We know it's a weak acid, so it's not going to make much product, so it's reactive. So now we're expanding beyond the simple rules of Chem 1A. We say, okay, we acknowledge that HF is supposed to be described as being mostly intact, but now we say it actually, to a tiny extent, does split apart, but now we're going to call it reactant favored. And we know what that means is that K is a really, really small number. K is less, a lot less than 1. And so in addition to that, we can write the equilibrium constant to the left. So in this case, what do we put on top of our fraction for the HF reaction? What do we put on the bottom of the fraction? It's going to be our products over our reactants. H plus at equilibrium times F minus at equilibrium over HF at equilibrium. So here's what's in our, now this is all just establishing. So here's what's happened before. Now it says, what would happen if solid NaF is added to the solution? So here's where the Chem 1A review comes into mind. What do we know happens to NaF when it meets water? It dissociates. Solubility rules. Sodium salts, sodium is an alkali metal, always soluble, so it'll break apart. So on the one hand, we'd say NaF doesn't actually appear in this, and it's a solid. We have to think beyond that. We have to think what we know about the properties of some of these things. So NaF is a solid, and it is not a part of this reaction. So we think it's not going to change anything. But then we can say, I know NaF splits apart. So as far as solubility goes, we'd say NaF solid, when it meets water, is actually going to go and make Na plus and F minus, which overlaps with the equilibrium reaction. So I've actually physically, geometrically put those reactions over each other to show them overlapping. So NaF will split apart into Na plus and F minus. And F minus is a part of the equilibrium. It increases exactly the concentration of F minus. So adding solid NaF, thinking 2 steps ahead, does impact the concentration of F minus. So the dissociation of this salt will cause the F minus concentration to increase, which is a part of the HF equilibrium reaction, what was going on previously in the beaker. So this disturbance will affect the right-hand side of the reaction. Too much F minus now. So what am I going to do? I'm going to shift to the left. The F minus will get used up along with an H plus to make more HF. So a shift left, less HF dissociation, and a decrease in H plus concentration will also occur. That's this reaction. This is called the common ion effect. Adding a salt containing a common ion, something that's in common with what's dissolved in the beaker and what's being added. So having a salt containing a common ion will affect the equilibrium. What we saw is that if I had a solution of HF dissolved in a beaker, if I add NaF, the dissolving NaF will affect the product side of the acid reaction. So we do want to think a little bit, I'm not going to say outside the box, but kind of. Just because NaF is a solid, and just because it doesn't match what's in the equilibrium reaction, isn't the end of the story. We have to think about what will NaF do when it meets water, and does the product that it make, does that affect? And in that case, we call this the common ion effect. A solid ionic compound meeting the solution will make ions. If that ion overlaps with the equilibrium reaction, then yeah, it will have an effect. NaF would, oh, interesting question. NaF, what would we call it? So NaF isn't considered a catalyst in this reaction. I would simply call it a disturbance. NaF causes a disturbance because it produces F minus. That F minus will get consumed. It'll get used up to go backwards. So catalysts need to be remade in order to be considered that role. So I would more so just say NaF causes a disturbance in this equilibrium reaction. But good question. Okay, our last example. This is an example of coupled reactions. Again, helpful to sort of flag this for experiment 1 as you look at that. We have solid NaOH is added to a solution of FeCl3 at equilibrium. What will happen? So an equilibrium solution of an ionic compound is called a saturated solution. So it's saturated with what can be dissolved. So what do we know happens when we saturate water with some, in this case, FeCl3 solid? It's going to dissociate. So what we're saying is, if this is at equilibrium, this will be our dissociated solubility reaction. So the first thing is, if I have an equilibrium solution of a salt, then my equilibrium reaction is the solubility reaction. FeCl3 solid makes Fe3 plus aqueous plus 3 Cl minuses. So yet again, we see an example of where our Chem 1A review is now going to be important to recognize what do I know happens when an ionic compound goes into water. That is going to be the basis of what's the analysis. It's going to be, this is our solubility equilibrium reaction. And of course, we know, along with the solubility equilibrium, if it's a reversible reaction, that we can write an equilibrium constant with an expression to go with it. So in this case, what will be the equilibrium expression for this reaction? We're going to take our products, multiply them, and raise them to their what? Coefficient. So coefficient. Fe3 plus at equilibrium times Cl minus to the 3rd power at equilibrium. Now here's something we haven't come across yet. So this is why I like this example, because it allows us to talk about this. What about what we put on the bottom? Don't we put concentrations of reactants on the bottom? The only reactant is a solid, which we were told not to put in an equilibrium expression. So what do we do? If there's nothing to put, then there's an invisible 1, or sometimes it is visible. So there's an invisible divided by 1. If we don't have anything to put on one side, we just put 1. So this would be it. So we have solubility reaction. We have a solution of FeCl3 at equilibrium, and we've written its equilibrium constant to help us figure out what's going to go on. And it says, suddenly we're going to add solid NaOH to the solution. And again, we might say, oh, but it's a solid. Solids don't count. We say, oh, hold on. It's NaOH. NaOH isn't in this reaction we just wrote. It doesn't count. You say, whoa, hold on. Yeah. Yep, you got it. So we have to think what beyond the simple face value of things. We say, yeah, okay, but what happens literally when NaOH meets water? And exactly right. We know that NaOH solid dissociates into Na plus ions and OH minus ions when it meets water. So at first, unlike the last problem, the last slide, this didn't immediately make it obvious what's going to happen. Because the last slide, we said, oh, it made something that was part of the equilibrium. This time, it didn't make anything that was part of the equilibrium. So now, again, we might say, wait a minute, does that mean that nothing happens again? And then, Michelle, you're exactly right. We have to think about these 4 ions floating around. What happens if they pair up? Does it make a reaction happen, particularly a precipitation reaction? Yeah. According to solubility rules, when an iron 3 ion meets a hydroxide ion, it forms a solid. So, oops. So an iron ion and 3 hydroxide ions will make a precipitation reaction happen, forming solid ferric hydroxide. So what does this mean? Iron ions are going to get used up to make a solid. So here's how we're impacting the equilibrium. Iron 3 ions are disappearing from the solution. So what will this reversible reaction do? It's going to try to fix it. So the reaction will shift to make more product. Yeah, more FeCl3 will dissociate. So we'll have a shift right, more FeCl3 dissolves to replace the lost FeCl3. This is an example of what's commonly called coupled reactions. Coupled means kind of like linked together, connected to each other. So these two seemingly different reactions are connected to each other because they share something in common. The Fe3 plus ion is made by one reaction and used by another. So there is a connection or a coupling between them. If my precipitation reaction goes forward, it will mess up my solubility and my FeCl3 will dissolve more to compensate for that. And we might see something like that in our experiment 1. So thinking about how seemingly adding things that don't take part in the equilibrium, they actually do matter. The very last thing quickly is I wanted to talk about catalysts and just how they come into play, because it can sometimes be a little bit confusing. Remember these nice things that we talked about and the visual we had using the reaction coordinate diagram. We said that catalysts help the reaction by lowering the activation energy. And with a lower activation energy, the reaction gets to the finish line faster. But one thing that we want to be careful with is there's a temptation to think that it does more than that. And the answer is it doesn't. It does not affect the equilibrium. It does not affect final concentrations. It just helps get there faster. So catalysts will help speed up the process, but it will not change how much product, how much reactant is there at the end. So just a quick tie back to our last lecture, catalysts speed reactions, but they do not affect how much you'll make at the end. It will be the same whether you use the catalyst or you did not use the catalyst. And so there we have it. Our first step into the topic of dynamic equilibrium. So we talked about the K, equilibrium constant, is a special ratio. It is always the same for initial conditions. Will always reach the same finish line, this ratio of products to reactions. That's why it's called an equilibrium constant. And Le Chatelier's principle, if we disturb a reaction, then the reaction will shift so that it compensates, but never undoes completely that process. All right, in our next lecture, we will continue the topic of equilibrium constants. This time we'll talk about the mathematical properties. So this lecture was a bit more conceptual in nature, and our next one will be the math behind equilibrium constants. So stay tuned with that. Okay, so hopefully this is our last lecture we'll have to do on Zoom. I know it's not ideal, as far as the communication portion of lectures. So we will, unless otherwise stated, be back on Monday. Things are looking pretty good in Pasadena. So with that, we'll go back to our regularly scheduled things. And I will update the class with an announcement on just a reminder about what things to expect when we come back with a weekend announcement. So make sure you're checking your announcements. I'll go ahead and make one of those tonight so that everybody's on the same page. And of course, if there are any questions about things, then please let me know. So I'll go ahead and turn off the recording, and then we can all have a good day.